Okay, so hello friends. This is the lectures related to career concentration, and yesterday we were discussed about the career concentration in related to electrons in conduction band, and today we will discuss about the career concentration, and that will be for holes, carrier concentration or carrier density, holes in conduction band, holes in valence band. So we will repeat the same terms which we have used in last lecture, and as far as that band structure is concerned, we have for semiconductor, this is the valence band, and this is the conduction band, separated by the forbidden energy gate EC, and this upper part, this is known as EC, the lowest energy value of conduction band, it is represented by EC, and the top value of this valence band, this will be represented by EV. And we have so many energy levels, and these are the energy states, and all these energy states are empty initially, let's say, and these are different energy states in the conduction band. And after electron hole generation, we will have numbers of holes generated in this valence band, and we will use the same terminology used in the last lecture. First one was we have used was that the density of state dE, and this is the number of states available, and in first case it was for electrons, and here this is available for holes to be occupied at an specific energy value, at any energy E. And this dE is multiplied by that is small energy range. So if we talk about that energy value E, then this is that density of states, which gives the states available for empty states available for occupancy of that holes here in this valence band. And when we multiply this by dE, then we will talk about one small energy range, this E plus D, this energy gave to dE, where we are just searching for those empty states to be occupied by holes, and this is the number of states available for holes to be occupied in the energy range E and E plus D. And then we have that Fermi-Dirac distribution function Fe. So here we will use that F for hole. So I should represent this as Fp or Fh. So this is Fh, this is Fermi-Dirac function for hole, and this gives which gives the probability of occupancy of holes at temperature, at a particular temperature T in any energy state. So at a particular energy state E at temperature T, the probability of occupancy of that hole, it is denoted by this Fermi-Dirac function, and this is for hole. So we have represented this by Fh, and we should know this Fe plus Fh, this is actually equal to 1. So for Fermi-Dirac distribution function, Fh as a function of E can be written as equivalent to 1 minus Fe, and and the function of E. We have used this Fermi-Dirac distribution function in our earlier lecture, last lecture, and today we will use this Fermi-Dirac distribution function in this calculation. And the next term which we used was the fourth one, NEDE, and this is and every calculation is in the per unit volume, because we are talking about the density or the concentration of these holes. So NEDE, this is number of holes now, holes per unit volume, occupied in the energy range E and E plus DE. So similar to this, if we just talk about that NE, then that will be that number of electrons per unit volume at a particular energy state E, and when we talk about this NE multiplied by DE, then that is actually the number of holes per unit volume occupied in this energy E and E plus DE. And so this NDE, it is calculated previously as this NEDE for hole. This is for hole. It is calculated as equal to density of state multiplied by Fermi-Dirac distribution function for hole, and this is DE. So earlier we have used this DE with this Fe, this is for electron, but here this is for the holes, and one can write this is equivalent to DE, and I can write 1 minus F for electron, and the E, and this is multiplied. And if you want to calculate the carrier density, then mathematically we can have so if you want to calculate carrier density, so therefore the carrier density or hole density, let's see, for holes in valence band, which is represented by NP, it is equivalent to, now we will integrate, and this NEDE, and integration will be, the limit of integration will be, upper energy limit is here, that is up to EV, and the lower energy value may be up to that minus infinite. So this is from minus infinite to EV. So this is the limit of integration, NED, and when we put this NED from this equation, one will have this minus infinite to EV and DE 1 minus F E D. Now we will further elaborate this equation in terms of this density of state as well as this Fe. So we will have where D, the density of state, is equal to 1 upon 2 pi square, and this is 2m by h cross square 3 by 2 root of E. This is for the simple general solids, and we will write this for that hole. So our holes in valence band, this DE can be written as equivalent to 2 pi square, and this is 2m. Here I will use mh, h for hole, and the effective mass of this hole, and by h cross square 3 by 2, and this energy value will be, upper value is this EV, and lower value that will be E. So I will write this as EV minus E. So remember this, there in case of electron we have used this is E minus EC, because that this EC, that was the lowest energy value, and E was greater than that EC, that's why we have taken this E minus EC, but here I am writing EV minus E. So this is the density of state for holes in valence band, and now this is equation number 1, and one can write this is equation number 2, and the Fermi-Dirac distribution function as usual, F epsilon E for electron, that is 1 upon 1 plus exponential of E minus EF by KT. So by putting this, we will have this 1 minus FE, E it is equivalent to 1 minus 1 upon 1 plus exponential of E minus EF by KT. So again, we will use the approximation for this Fermi-Dirac distribution function term this, and this is for whole now as a complete. So one can write this is 1 minus 1 plus exponential of E minus EF by KT, and inverse. So again, if we know that from polynomial function we will have this 1 minus x to the inverse, that is equivalent to 1 minus x plus x square minus x cube plus x4 and so on, and the hat terms can be divided, and this 1 minus x inverse is equivalent to 1 minus x we can write. So in place of this 1 plus exponential of this, we can write 1, and x is here this minus this, and the final term will be, we will have, so finally this implies 1 minus Fe, that function of t is equal to exponential of E minus EF by KT. Check it. So this is 1 minus with minus and this 1, and this will be with 1 minus x. We will take this only 2 term here. So 1 will be cancelled, and we will have this exponential of E minus EF upon KT, and this is that approximation. So by putting these two values, that one is the density of state for holes, and this Fermi-Dirac distribution function for hole in that the equation number 1, we will have from equation 1, now we will have this NP, that the density of carrier density in the hole, that is from, it was minus infinite to EV, and density of state is, that is 1 upon 2 pi square 2mh involved h cross square, and this is 3 by 2 multiplied by root of EV minus E multiplied by this Fermi-Dirac distribution function E minus EF by KT with respect to dE. So this is the whole integration term, and we have to solve this. So initially, as in carrier density for the electrons, we have converted this equation in that gamma function term. So we will try the same here. So before that, we will keep this as a constant. So this can be rewritten as equivalent to I should write here B. So minus infinite to EV, and this exponential E minus EF by KT multiplied by root of EV minus E, and multiplied by D. This is the term. So again, this EV minus E is here, and here E minus EF here. So we should have this term in this exponential part also. So let us make some modification, and here I should write B is equal to that 1 upon 2 pi square, and this is 2m star mh star by h cross square. This is the 3/2, which is the constant. So let us make some modification here. Let us make some modification. So b minus infinite to ev and e, and we need ev minus e here. So exponentially we should have this ev minus e. So this is in the positive term, so we should write minus term here. So this minus this becomes a plus, and this is with minus sign. So minus ev, so this is plus, this is minus, and this is this ef. Check it. So let me check. This is e minus ef, so ef minus e. Just I have inverted this with minus sign coming out from this bracket, and this ev minus e I need. So this ev minus e is here, so ev minus e, and this is the term, and multiplied by root of ev minus e, and this is here, and the limit same. So one can write this is actually equal to b multiplied by, now we will divide this term into two parts. One part corresponding to this ev minus e, and this is and the second term, that is this term ef minus this. So exponential of with minus sign, and this ev is the higher term. So this is ev minus ef, sorry, ef minus ev, because Fermi energy level is somewhere here. So this is ef. So ef is greater than ev. In the first term, when in our earlier calculation we have taken this as ec minus ef, and the reason is because ec was at the higher energy level with compared to this ef, but here we will put ef minus ev here. So this is minus sign, ef minus ev, and multiplied by minus infinite to ev multiplied by exponential of this minus ev minus e by kt. So this is by kt, and here also by kt, and multiplied by d. So this term, this is that integration term which we have to convert in form of gamma function, and this is the constant as usual, because Fermi energy level is constant, and this upper energy of this valence band is also constant. So this is the constant term, and we will convert this in gamma function. So let us try to there should be one, so that e v minus so let us try to use a substitution method. So by substitution we have let ev minus e by kt it is equal to x. So this term is taken as equal to x. So this implies minus de it is equal to kt multiplied by dx, and we will also change this limit here. So if that this energy E tends to minus infinite, then this implies x tends to infinite. Remember this here, where ev minus e by kt is equal to x. So when this e tends to minus infinite, this minus sign is here, so this x tends to infinite. And if this e is equal to, it tends to ev, means that energy is up to this higher energy level, then with this minus sign this implies x tends to 0. So the limit will be, so this limit will be from infinite to 0. So NC will be carrier concentration, carrier density in valence band, that NP it is now equal to this constant B exponential of minus EF by minus EV by KT, and let me put the value of this and this and this. So limit is in between, this is from infinite to 0, and exponentially minus x, and this root of this is root multiplied by x, and also multiplied by kt, because of this EV minus E by kt is x, so this is equal to multiplied by kt, and this dE is minus kt dx. So let's use the simple mathematics now. Just keep that minus sign here. B exponential of EF by the limit is infinite to 0, e to the power x, and this is root of x. So I should write this x to the power half and kt to the power half multiplied by kt and dx. So now I am trying to take this minus sign here, and just I can reverse this limit of integration. So this is b exponential of e phi minus this by kt, and this kt to the power half multiplied by this kt can be written as equal to multiplied by kt 3 by 2, and this is 0 to infinite x ex multiplied by x to the power half dx, and this is that the gamma function. And so from gamma function, so in spite of physics, mathematics is much more here, so we will use gamma function now. So from gamma function, this is defined as equal to integration, the limit is same, 0 to infinite e to the power minus x, x to the power n minus 1 dx. So this can be written as, this implies integration of 0 to infinite e to the power minus x, x to the power half dx. This is equal to gamma of 3 by 2, because n minus 1, when we compare this by half, then n minus 1 is equal to half, so that is equal to n is equal to 3 by 2, and since this gamma function of 3 by 2 is root of pi by 2, and we have taken in our previous calculation also the same value, and we will put this gamma function is equal to root pi by 2 and all other constants here. By substituting these parameters, and the constant value b will have this np, it is equal to, we will put that value of b is 1 upon 2 pi square, and that was 2 mh star by h cross square 3 by 2, and then exponential term is that exponential term, and this is with minus sign ef minus ev by kt. There is one kt term, kt 3 by 2, and this gamma function is root of pi by 2. So the value of gamma function is here, that kt term is here, and this exponential term is here. And now just try to rearrange this function. So by rearranging, so now I am trying to rearrange all this. So np, it is equal to 1 upon 2 pi square, and kt is also the power of kt is also 3 by 2, and this is also 3 by 2. So this is 2 mh star kt inside this, and I'm taking this h cross is equivalent to h upon 2 pi square, okay, and this is 3 by 2 multiplied by exponential of, that is root of pi by 2 and exponential of minus EF minus EV by kt. So this is equal to 1 upon 2 pi square, and this 2 pi can be taken out from the bracket. So this is 2 mh star kt by h square, and this is now 2 pi cube, because this is in square here, this power is 3 by 2, and this is root of pi by 2 exponential of minus EF minus EV by kt. So this is the 2 pi square, this is 2 pi cube, and there is one 2 is here, and that is root of 2, and we will get this is equal to 2 times 2 mh star, and we can also put this pi inside this, that is kt by h square and 3 by 2 and exponential of minus EF minus EV by kt. And this term is, all these terms are, this kt at a particular, this term is a constant. At a specific temperature, this is the constant, and it can be represented as Np, and exponential of minus EF EV by kt, where Np, this is equal to 2 times 2 pi mh star kt by h square 3 by 2, and this is known as, effective density of state of holes. So this is the effective density of hole, density of states of hole in valence band. So finally, the final equation we have is Np, this is equal to capital Np exponential of minus EF minus EV by kt. This is the final expression where Np, it is equal to 2 times 2 pi mh star kt by h square 3 by 2, and we can compare this with that carrier density of electrons in conduction band. So, and we also have n e, that is equivalent to nc. One can write this multiplied by exponential of minus, in terms of this is EC minus EF by kt, where Nc, this is equal to 2 times 2 pi me, the effective mass of electron, multiplied by the same temperature and that Boltzmann constant kt by h square 3 by 2. So the difference is here, this is effective mass of hole, this is effective mass of electron, and this is that effective density of state for electrons in conduction band. This is the effective density of holes in valence band, and the expression are just similar. But remember that this is EF minus EV, because EF is at the higher energy level with compared to EV, and this is EC minus EF because this EC at higher energy level with compared to EF, and we will use this relation in our further calculation. So students should do some practice to get this result. Thank you.